Okay, let's get started. So hello everyone, my name is Tianqi Chen. So today I'm going to tell you a bit about our recent effort in Apache TVM and this general effort on deploying large language models with universal ML compilation. So it's great to be here and talk about machine learning compilations. And we've been working on ML compiler for several years now, and it's great to see ML compiler starting being used in a lot of places. But one of the things to recap and when we think about this field is what are the biggest challenges? And I think our earlier speakers also alluded to that in a sense that when we are doing machine learning development and machine learning engineering, the biggest challenge is not only trying to build a solution for today, but continuously to keep up with, hey, I have a new model, I have a new demand, new customization coming in, and you want to be able to keep up with that. Right? That's the biggest challenge in here. Today I'm going to talk about 3 high-level thoughts that are related to machine learning compilation constructions. We're also going to talk about the specific domain-specific compiler we are building in the past 1 year. First point is that we want to think about machine learning compilation research and development. As of now, can be quite different from traditional compiler development in a sense that traditionally, if you think about compiler, you developed it for several years, you ship it, right, and then you make use of it for effectively quite a while. And if you are a machine learning scientist, what you do is you go and develop a mature framework on top of, develop your models on top of a mature foundation. You don't care about the black box. It's going to go and work for you. However, I would argue that machine learning compilation development itself should be more productive in a sense that, why don't we go and build a language model compiler in a month? And, if you can do that, that allows you to be able to go and iterate together with the model development in some sense. And with a lot of the new emerging workload today, actually, we are getting into, we are seeing need of, hey, we can build a specific solution for a particular model or a particular kernel model. Right? And the really bottleneck there is actually the machine learning compilation infrastructure need to learn a lot from actually machine learning frameworks where, with PyTorch, you will be able to define your new model and run it in a day, right? And ideally, we should be able to start building some of R&D toward that direction. So one of the lessons we learned so far is we would like to actually make Python as a first-class citizen in ML compiler development. So the idea is that we want to be able to embed most of our unified IR within a Python AST, and you will be able to go and manipulate a lot of that. Additionally, you want to build modular composition transformations in Python if necessary, and if you find them being useful, you put them into C++ or more mature language and make it more efficient, right? And in that sense, our development looks more like this. You have existing pipeline that works well hopefully for most of the use cases. You start to look at a new model, maybe, okay, hey, I need a new attention operator, right? Previously, you need to go to your C+ code base, you dig into okay, here's the place I lower attention, I go and hack that code, and then you maybe after months you ship it, and then you observe a performance gain, or maybe you get a feedback, or this is not really what we want. Right? So instead, what we really want is you start to introduce Python-based pipeline libraries. You say dispatch to my attention, and customize your pipeline, and then you compose it with the rest of the pipeline, ideally. And it gives you immediate feedback. Maybe that particular path is only working for one particular model, even. But if it doesn't take 1 day, you customize a pipeline, you ship it. If it works, that's great. If not, let's come back and reiterate. So that's a high level. In terms of, we really want to be able to make ML compilation development more productive and making it as part of our machine learning engineering pipeline. The second thing is about some of the high-level lessons we learned on building the intermediate representations, specifically along the cross-level abstraction and first-class dynamism. So first of all, a lot of our talks today also mentioned about different levels of compiler abstractions. For example, if you want to look at a kernel language, usually kernel language at what we call loop level or tensor program level that describes high-level loops, loop nestings, and GPU thread bindings and so on, right? And we also talk about graph compilers. In a sense, you have a graph, computational graph node, where each of the node contains high-level tensor operations and so on. Usually what we do is we start with graph-level compiler. You optimize it in graph level, and you lower it into the kernel level, and you go and optimize them. What we really found is actually helpful to try to bring them together in a more organic way. And specifically, you want to be able to both analyze the loop level program to automatically provide you annotation, which otherwise you have to manually annotate for each of the computation graph node, as well as do some cross-level transformation. So I will, because of time, I'm going to show one particular case study, which is, if you support language models, you want to look at different kind of quantization format, like AWQ, Q4, FP8, FP4. And the first problem you will find is that, if you start working with a compiler, it does not support that particular quantization format. It's very common. Like I think I faced that when we start our old compiler pipeline. So if you have a cross-level representation, what you can do is actually we can use a lower-level tensor program to directly represent, hey, here's how I'm going to decode a Q4 into my floating point. And then ideally, if you can create a cross-level optimization that automatically fuse the low-level tensor code with the original MATML code and do certain manipulation and so on. So having cross-level really brings some kind of flexibility. Of course, this still is possible if you go and change your compiler, introduce a new data type, introduce operators, introduce lowering rules, and so on. But with this cross-level thing, we'll be able to add that in one day. Okay. The second thing we find is really helpful is really want to bring first-class symbolic shape. Because language model, you have dynamic shape, both in terms of batch size as well as sequence length and so on, right? And there are two different kind of ways normally you handle this. So first way is you try to do what we call any shape. So you have a dynamic shape dimension, you mark as a question mark, I don't know what it is. Symbolic shape means that you have a symbolic dimension n. After I flatten it, right, it's n by 4. After flatten it, it becomes n times 4. So compiler will be able to reason about their relations. Like I will be able to tell that the number of elements here is going to be the same number of elements in the second part, right? So as a result, maybe in memory allocations, I will be able to tie them together because they have the same number of elements. So bringing first-class symbolic shape is really useful, but it's also really challenging. Specifically, in our case, we really want to not only target just-in-time compilation, but also ahead-of-time compilation. So we want to be able to target full program, right? So that means that we want to be able to enable global checkings, including having function signatures that contains like high-level relations, like I'm taking a tensor by n by 4, and after calling, it gives you tensor by n times 4. And additionally, you want to be able to propagate these symbolic shape relations, both in terms of the computation graph level, as well as your low-level tensor level, right? So that gives you better information. Okay? So with all that element together, I want to talk about the specific use case we have been building. The use cases we really want to be able to enable deploying large language model universally across different environments. And to be clear, this is not a general purpose compiler. This is a specific MO compiler developed for language models, built on top of the compiler infrastructure I talked about in the first part. And MOCM is, as of now, it supports all the hardware targets in here. You can run on Windows, Linux, Mac across platforms. It has an OpenAI compatible server that gives you, allows you to run different models. It runs on iOS. If you go to the App Store, search for MOC Chat, you'll be able to find a demo app that can run Llama models and other small language models directly on your iPhone. It runs on Android. You can bring it to a $100 Orange Pi device. It runs on Steam Deck. If you want to play games. And additionally, we are also building a unified engine for doing additional things like efficient structure generation, where it has built-in support for JSON grammar and gives you new zero overhead generation here. And one of the goal, again, is we really want to be able to unify the overall compilation and generation for both cloud cases and edge cases. So far, I've talked about a lot of edge cases. More recently, we have been also working on some of the low latency server optimizations. So in this particular case, it's a low latency server benchmark, checking, in this case, we are talking about both in terms of throughput, higher is better, and this output token part. A lot of benchmarks recently in server focus on throughput, which means that you want to push the batch size to be as large as possible so that you can utilize the GPU as much as possible. However, most of the GPU providers, most of the language model providers also care about output tokens, right? You really want to give your users as fast a response as possible. So really what you want to look at, for example, if you want to have your output token to be above 100 tokens per second, you want to look at something like everything on the left-hand side of this line is useful. And you can find that with enough optimization compilations, you can get pretty decent performance, as good as what's the best out there on the server cases. And you can also make it run on most of the environments. One of my favorite examples is you can go and directly run on web browsers. Actually, I'm going to show a live demo now with last 1 minute. So if you go to chat.webm.ai, you can directly say, tell me,
about PyTorch, given this is a PyTorch conference. And what's going to do is, it's always a danger to show live demos. Let me refresh. Try again. And you can try it on a laptop as well. And what I try to do is we're going to fetch the weights onto a web browser cache. It runs all locally on my laptop. And it's being populated by its Llama model, by the way. Thanks, Facebook. It compiles. Actually, the MOCM compiles it to WebAssembly and Web GPU, so you can see it run pretty fast. And actually, you just need to open a web page to run. Okay. So that's and coming back to the presentation. So yeah. So overall, all the materials in today's talk you can find in this website called MOCM.ai. I'm also really passionate about actually making machine learning compilation more accessible and learn more about it. So I'm creating a course about ML compilation in general. And the overall specific domain-specific compiler MOCM is going to be available on that website. Okay, hopefully I'm just in time.